So I'll talk about transience and non-ergodicity in a model of many Sokobans and boxes on a line, and this is joint work with Deepak Dhar. So, so I believe some of you might be familiar with this game Sokoban. So this is a box pushing puzzle video game which involves a Sokoban player or a warehouse keeper pushing boxes through a warehouse, trying to get them to these earmarked storage locations. So, so these are fixed walls which are impenetrable. And at any time, the Sokoban can move to one of the empty neighboring sites or to a box occupied site by pushing a box to the empty site that is next to the box. So from this position, the Sokoban can move up or down, but it cannot move here because this box cannot be pushed to the next site. But it can move over here and then push this box down and then move to this site. So the Sokoban can either jump to an empty site or push a single box at a time. So, Bonomo and Ruvini considered a random walk model based on this game. So they consider a graph G in which each site is independently occupied by a box with some probability Q, and a random walker starts at a specific site and performs a Sokoban random walk. So the random walker moves at any time the random walker moves to a nearest neighbor empty site. To a nearest neighbor site that is either empty or has a pushable box. So these are some earlier works on this model. So these involve a single random walker on some graph. So Prashant Singh talked about this, about his work on Z2 on Monday. So we are interested in a variant of the Sokoban random walk model. So our model involves multiple Sokobans and boxes on the integer lattice. So we consider a line of L sites where each site is occupied by a Sokoban, occupied by a box, or is empty independently and with equal probability. And so on the outer boundary, we will consider some fixed impenetrable walls so that the Sokoban or box cannot move past these empty site, these boundary sites. So I also consider a continuous time Markovian evolution of the system, where each Sokoban attempts to make a move at some rate, at some positive rate mu, independent of others. And these are the successful moves. So if the Sokoban attempts to jump to a empty site that is next to it, then the move is successful. Or if it is trying to push a box to an empty site next to the box, then the move is successful. So this involves pushing a box to the right, and this involves pushing a box to the left. So this is an interacting particle system with which shows transient states, strong ergodicity breaking, broken detail balance, and non-equilibrium steady states, and it also shows aging. So the system, due to the presence of transient states, the system gets shrunk as it evolves. So first and it also gets more and more fragmented as it evolves. So we start by asking what's the number of disconnected components in the entire configuration space to begin with. So I'll say two configurations are in the same connected component if there is an undirected path between the two configurations. So to count the number of totally disconnected components in the whole configuration space, we need to consider a slightly different dynamics, which involves pulling a single box in addition to pushing a single box. So for this dynamics, it turns out that the conserved quantities are the relative positions of boxes and Sokobans on the line, and the positions of the boxes that are not adjacent to a Sokoban. So these are the conserved quantities for the dynamics which involves pulling a Sokoban in addition to pushing a Sokoban, and this gives the total number of conserved quantities in the system, and the number of conserved quantities gives the total number of mutually disconnected components in the configuration space. So we can also write a generating function for the number of mutually disconnected components as follows. So if we expand it in a power series, the coefficient of the term z power L gives the number of disconnected components in a system of size L. So we can also we can also find the asymptotic growth rate of the number of mutually disconnected components by looking at the radius of convergence. So DL is the number of disconnected components in a system of size L, and we can compute the compute DL for a large system using this radius of convergence. Okay, so now the next thing I want to look at is recurrent and transient configurations in the system. We say a system is, a configuration C is recurrent if starting from C, the system will eventually return to C with some probability, with probability 1, and it is said to be transient if starting from C, there is a non-zero probability that the system never returns to that configuration. So, these are recurrent configurations. So whenever there is a single box which is sandwiched between two Sokobans, so one of these Sokobans can push the box. If one of the Sokobans pushes the box, then the other Sokoban can push it back. So it is possible for the box to come back to the same position by following these sequence of moves. But if we have at least two pushable boxes between Sokobans, then if one of the Sokobans pushes the box to this empty site, then the box is frozen at that site and it cannot get back, the system cannot get back to this configuration. So this is a transient configuration, and we will call an empty site into which a box can be pushed into and pushed in an irreversible way, a contractible empty site. So this is a contractible empty site. So we will define a notion of height for a configuration to be, and I define height to be the number of contractible empty spaces in the configuration. So for example, if we look at this configuration, so this Sokoban can push this box here, and since there is no Sokoban to push it back from the other side, this box will be frozen here. So this is a contractible empty site, and say this Sokoban pushes this box here, then this box will be frozen because this Sokoban cannot pull, neither can this Sokoban push two boxes. So this is also a contractible empty site, and this is not contractible because once this box is pushed to the side, the Sokoban can push it back to its original position. So this is not contractible. So this configuration has two contractible empty sites. So this is the height of the configuration. So based on the height, I can get a decomposition of the configuration space into different levels. So the level, so each dot here represents a configuration, a whole configuration, and so a configuration, all configurations here have 4 contractible empty sites, and if we look at a configuration here, it has no contractible empty site and it's called a recurrent configuration. So we can count the number of configurations at height h by using a generating function, a multivariate generating function as before, and I can also look at the number of configurations at in the thermodynamic limit by fixing the contractible empty site density, and this is the function of entropy, level-wise entropy. So this is log of the number of configurations at a given level. So this is as a function of contractible empty site density, and we see that the number of recurrent configurations, which is this exponential of this number here, it grows as e to the 1.0986 times L. And one can also show that the number of contractible empty sites in a typical configuration grows as L by 16 for large L. And as the system evolves, it also breaks down, it also fragments further. So at the top level, there is only one component, but as it evolves, it breaks into further components. We call each of these components intra-level connected components. And so once a system goes down a level, it cannot go back to a higher level. And there are arrows. So within an ILCC, intra-level connected cluster, all configurations are connected. It is possible to go from any configuration to the other. So what we are interested in is the number of configurations that are accessible from within an ILCC. So this is So this is given by e to the s restricted, s is the restricted entropy per site times L. So we find that the restricted entropy grows as 0.3182, and if we take the average over all configurations, and the average size of a recurrent ILCC here grows as e to the 0.4103 L. And earlier we saw that the number of recurrent configurations, if we look at all the configurations at this level, the entropy of the number of all recurrent configurations is 1.0986 as opposed to this restricted entropy 0.4103. Now this is this is a plot of the contractible empty density versus the restricted entropy. So I start with different initial configurations and run different trajectories, 5 different trajectories for each initial configuration. And I have plotted the contractible empty space for each trajectory and the density, the restricted entropy as a function of the contractible empty space. So we see that the entropy increases as we go down a level, as the density of contractible empty sites decreases. And so the system also exhibits aging because the number of, as the system moves down a level, the number of attempts required to move one level further increases. So the number of contractible empty sites decreases. So to move down a level, the system, a Sokoban has to push a box into a contractible empty site. So the number of attempts required will increase. So this causes aging in the system. So this is the summary. So I defined the model on 1D lattice, and I looked at the connectivity structure on the configuration space, and I gave a quantitative description of transience and non-ergodicity and show that the system shows aging. Thank you.
Any questions?
So this reminds me of this something called activated random walks, in which this particle can hop only if there's a hole at the back.
Okay.
So like if your particle is moving when there are two boxes,
Okay.
and one box moves, then it's sort of like that, no? So I'll just tell you the activated random walk is that the particle can move if there's a hole in front, but also a hole at the back.
Okay.
So and that has been studied a lot.
This involves pushing?
Yes, but like the box if the particle is moving, that means box is moved to the opposite side, and that is possible only if there's a box at the back.
Okay.
I mean, probably I'm not clear, but maybe I'll just tell you again. Okay. But in case you want to look at it again, because I think a lot has been studied about that model also.
Okay. Okay.
So sorry, I don't remember completely.
Okay, I'll ask you later.
Any questions? If not, let's thank the speaker.